So I'm here today actually to, first of all, I'm very glad to be here, and I'm here today to tell you, to talk to you about how it all started for Hydro-Quebec. How did we start caring about resiliency, climate adaptation? What did we do about it? How come we have our own research team on resiliency? What are some of the works that we did? And although it says a scientific approach, I have zero equation and zero formula, so sorry to disappoint the PhD student here, but I'm gonna go through some of my material. I might skip some of the slides because it depends on the time that we have, and maybe leave some for the Q&A sessions. All right, so if I want to talk a little bit about Hydro-Quebec first, so we're one of North America's largest electric utility. We generate 99% of our power from clean renewable energy, that is water-based, hydro-based. We own and operate 63 hydropower plants with an installed capacity of 37,000 megawatts. We own and operate an extensive transmission grid that will total 34,000 kilometers. And we, of course, provide the electricity for the whole province of Quebec. We do some exportations to, of course, neighboring markets in Canada and in the States. One of our mission basis includes like delivering clean energy, reliable energy that is resilient to extreme weather events and to climate change. And this is where I'll be talking about in the next slides. So how it all started, actually, it started by Hydro-Quebec and the province of Quebec living a couple of sad and bad events, starting from a dam rupture in 1996 in Saguenay, followed by a couple of years later, 1998, an extreme freezing rainstorm under which power lines broke, towers and pylons crippled under the weight of the freezing rain. Also, we lived and witnessed a series of years with low precipitation and water availability. And how come we didn't see that coming? What's happening? All the signals indicate that we're going to have a lot of water in the future. How come we have, 4 or 5 years of lack of water and energy in our reservoirs? So all of this, made us start to think. And what happened after is that we've been all over the news since then. So since then, at that time, let's say before those events, people maybe barely knew about Hydro-Quebec. Now it's all over the news. Believe me, the slightest branch will move, touch a power line, and we're on the news. So then we said, okay, we need to do something about it. And we realized actually that we're vulnerable to some main weather hazards and the climate risks. So in the center, we're vulnerable to wildfires. In the north, we're vulnerable to the thawing permafrost. On the coastal part, where there's the erosion and storm surges. So we have a couple of vulnerability towards certain climate and weather hazards. So what can we do? We said there are two things to be done, okay? It's either we can reduce and or we can adapt. So those are the two facets of climate change fighting. It's either you reduce or you adapt. So reducing, as you know, it's usually international agreement, government policies, targets, and it's not to Hydro-Quebec to reduce by itself. So we just go with government decisions and international agreements. But the thing that we have control on is to adapt, of course, and learn how to live with a changing climate, how to be more resilient, and prepare our grid and our generation system for that. So now that we know that we want to adapt, okay, what can we do about it? So what we did actually is that we created and we co-founded Uranos. So Uranos is actually the extension of Hydro-Quebec's Research Institute, but that only focuses on climate change. So Hydro-Quebec, with the government of Quebec, and later on several other partners joined, founded Uranos. Maybe you've heard about it. It's Quebec's main research institute on climate change, and it's starting to have also being renowned worldwide. But the problem, not the problem, the thing is that Uranos, their mandate and their mission is to focus on climate change, so on the really long term. So what's going to happen in, in the 2070, in the 2100 span of time. So it's projections and not forecasts, right? But we still needed to do forecasts on the short term, on the midterm of, the events that will impact us. And so, where we're at, exactly. So in able to be able to meet our adaptation needs, in order to be able to meet our resiliency need, we needed to create our own research team as well. So our own research team, what does it do? First of all, it works closely with Uranos. We work hand by hand. They're our main partner in anything related to resilience and climate adaptation. But us, our team, what we do is that we work with global models, climate models. We enhance existing ones. We develop and enhance weather forecasting models on the short term and on the midterm. And we have other, let's say, emerging technologies coming that we're exploring as well that I might talk about during the Q&A period. So we work with observations, we work with forecast models, and we work with climate models. And this information actually is the output of those models, is the main input to the key resilient decision that our business units are taking. So we're taking decisions that are scientifically based and scientifically proved. That's the strength and the goal of our research team and the reason of being. So we do generate different type of information. First of all, we do generate and produce basic information, and basic information basically is used to create awareness mostly, right? So just to tell people in upper management, hey folks, there's climate change, it's coming, you can see projections in wind, temperature, whatever. And then we create intermediate types of information. Intermediate type of information basically is based on thresholds. So let's say, how many, if you compare the summer 10 years ago versus summer in the next 30 years, how many number of days we're gonna have above 32 degrees, okay? How many freezing cycle are we going to have? The vegetation, how much is gonna grow per day per degree, okay? In the summer between 2070 and 2100 versus today. So intermediate information basically is based on thresholds, and it can help take, of course, some decisions based on if we're meeting a certain threshold or not. I'm gonna jump to examples later on. And then you have the advanced information. Yeah, so the advanced information basically is the information that comes out of what we call impact models. So let's say stream flows in terms of, what are the flow that are going into our hydropower plants? Are we gonna have enough? Are we gonna have extreme floods? Are we gonna have, for example, we do produce the intensity, duration, and frequency curves for different weather events, precipitation, snow, wind, freezing rain, and so on. So those are what we call impact models, and the output of those impact models are used to take key decisions. And the thing is, the more complex the information, the more it's beneficial to the company, of course. So this is where, first of all, the key adaptation and resilience decisions are taken with this and with those information, and this is where it makes us save and gain the most in terms of benefits, financially speaking, I mean, right? So I'm gonna jump into some examples, and I might, skip a few as well. We're okay on time, Robert? Yeah, okay. Perfect. So, for example, with basic information, although it's used for awareness, but we could use temperature forecast, for example, in order to forecast, in the next 20 years, 30 years, whatever, what will be our demand, right, in the summer, for example, with the increasing temperature. So it's based on basic information. In terms of intermediate temperature information, it becomes more interesting. We talked a lot about fires today, right? So this is, as I said, the basic intermediate information is basically it's thresholds, right? So we created, I will look at the last point, which is the wildfire. So we took an area of study, and now we are generalizing it over the province, but we took an area of study on which we overlaid all of our assets of, like, let's say, our hydropower plants, our transmission line, our distribution lines, right? And then on this layer, which is in La Grande, which is in northern Quebec, we overlaid a probability, a map of probability of wildfires, okay? Which is this. So now we know where's the area that has the most probable wildfire of happening. It's not time bounded. It's just in the next year, those areas are probably are gonna burn at some point, right? And you know how close it's to our hydropower plant, to a power line, to a switch yard. And this probability is based on the forest age. It's based on past fires. It's based on weather forecasts in terms of wind, rain, precipitations, and so on. And we're able to generate this map. And this map, actually, we update it every year. So it was the first time we generated it was in 2022, I believe, or 2021. But then in 2023 and 2024, we do update it. So what we do, we overlay on top of it the real fires that happened. So you can see here, for example, in purple, those are the fire that happened for real in 2023. And in light blue, there are like two small circles in light blue. Those are in 2024. So we had a very bad year in 2023. And as you can see, the fires happened in the areas that we said there is a probability of a fire happening, right? And now what we'll do next, which is not done here, we will update the probability map with knowing what is or what has already burned, because if you remove what has already burned, the probability in the whole area is gonna change. So this is the update that will be coming. This is an information that's done with the basic information, right? And just one last example, okay, I'm gonna skip this one, I'll talk about it later. With the more advanced and complex information, we're developing a model that predicts power outages that are caused by extreme weather events. And in this model, you can see on a map the forecast of the next, extreme weather events in the coming days, and where's the area that's going to have the most severe power outages. And this will serve for two purposes. First, to decide when to send the troops on the field that are going to do the reparation and reestablish the current. And second, if it's safe to send them to do so because of certain threshold. Is the wind speed safe? Is the rain intensity safe? And so on and so on. So basically, what I'm gonna end with is go to the end and whoops here. It's important that adaptation measures and resilience measures be based on scientific information, on data that's clean, that's validated, because any model that does forecast or projection, whatever, if you put, I would say, garbage in, garbage out, right? So data and scientific proven data is the key to this. I think I'm gonna stop it here. Great, thank you.
Okay, thank you everyone, and it's a pleasure to be here. I also have the dubious honor of being the only consultant on the panel, so I'll try to keep the sales pitch to a minimum. But I do think this brings a good advantage because I'm going to talk a lot about some of the things we're seeing across the industry, across the world. We're talking mostly around a North American perspective right now, but what we're seeing here is happening everywhere. I'm going to focus on some North American examples about some of these technologies that we have, but I'm going to jump into a few other examples that we're seeing globally. Just quickly for Hatch, where I sit is we're Metals, Energy, and Infrastructure Company, and I lead the group called eGrid. And eGrid takes care of our renewable power transmission and our distribution and smart grid. So that gives us a very unique insight into grid resiliency, extreme weather events, and how we're going to manage those. We see a lot of overlap between these three areas and how we're helping our clients solve some of these extremely difficult problems. I was actually amazed when I read this statistic that 83% of the reported outages, and this is through the DOE, between 2000 and 2021 are weather-related. More surprising is that weather-related outages have increased 80% since 2011. So this is a direct correlation to what everyone's seeing day to day in their lives. There's some very recent examples. I'm based in Winnipeg, or just north of Winnipeg, and everyone knows about the wildfire issues we're having. It's the worst one we've had in 30 years. And I got a really interesting personal example I'm going to show about what impact does that have, and what do these wildfires have an impact beyond what we talked about this morning about the impact on infrastructure and what's going on. We also talk about extreme cold in Alberta that almost collapses the grid. I think that was last year that the power system came within 10 megawatts. And think about it, 10 megawatts of collapse. They were phoning people to turn off their chargers. Like the criticality of how bad that was sort of talked a little bit in CBC and then but that is a huge issue. And this is one of the areas I want to talk about a little bit more, is that they relied very heavily on some interregional transmission that if the capacity was bigger, we wouldn't have been in a situation that we're seeing. I want to talk about a real-life problem. Again, I'm from Winnipeg, about 200 kilometers east is a small town in northern Ontario called Kenora. I have a small fishing cottage on an island off-grid that I built, completely solar energy storage. And people know me. I actually have created a PSCAD model of my network that shows the toaster impact. But what I want to show is the picture to the left and the right. This is taken a day apart of a wildfire. On the left is a normal sunny day. On the right is when the air quality index was at 11. You can see a little bit, it's maybe hard to see in the background, you can see the transmission line, which is the main intertie between Manitoba and Ontario. It's the K22W line. You can see it in the left, but you cannot see it in the right. Okay, this fire is 500 kilometers from the location of where my cottage is. Again, looking at some practical data, what you can see on the left and what you can see on the right is my solar system because of the smoke impact. We talk about distributed resources in a community, which I think is extremely important to help with the grid reliability and resiliency, but we have to go beyond that. You can see the wildfire smoke on a perfectly sunny day impacted the capacity of my solar system quite drastically. And you can imagine if we had a whole distributed resource system working, or a solar system working off of this that was feeding a single entity, it would cause a major issue because of things like this. So when we're thinking about some of these wildfire issues, we have to think about beyond the immediate impact of the fire, but the smoke and the coverage of some of these thermal issues is a real deal. The other thing is the smoke, it decreases the effective insulation of the transmission lines. It didn't impact the line, thankfully, in this case, but if the smoke is coming through, it's a pollution factor that a lot of transmission systems are not designed for, and we have to start accounting for some of these things. But again, this is just a very practical example that I saw that really hit home to me, because you hear a lot about these issues, but I wasn't really able to put them into a real context until I saw this. But there are a lot of things that we can do. We talk a lot about smart grids, using AI, using technology. How can we predict what's going to happen? Distributed energy resources. This is going to be an extremely important part. And going back to my last example, that was one example that didn't work well, but I wouldn't call myself a distributed energy resource because I'm not connected to the grid. So it was mostly an impact I had on my own. But if you take a look at what BC Hydro was doing. They're building 7 of these distributed energy resources microgrids across the province to help mitigate some of the issues they're seeing. We have microgrids, and talking about cold weather, this is when people say you can't do a lot of microgrids in solar and cold weather, This is an example of Raglan Mine, north of the Arctic Circle. It's a microgrid with a solar, wind, energy storage, and a small diesel. Right? We have the ability to do these. And this is one of the things that I come across in the industry, especially because we're going across the different sectors, is a lot of the solutions we have already. We just have to start thinking about applying them in a different way. You know, if we look at these are more micro level solutions, I would say. If we take a look and we take a step up, and this was talked a little bit in the panel before lunch about what WEC is doing and what NERC is doing, is, you know, what are some of the technology we can look to help on a macro level? And this is, I think, one of the most important things that I hope comes out of some of the political tensions we have and some of the promises of the government about building a better ability to build energy corridors east to west in Canada. And when I hear energy corridors east to west, I don't think of pipelines, I think of transmission lines. Right? There's two great examples that are happening right now in the US. One is just south of Manitoba and south of Alberta. It's called the North Plains Connector. And what they're doing is they're actually looking at connecting two operating entities, MISO and WEC, across and using the time shifting of these entities to allow interregional transmission. So what does that mean? The wind blows west-east, sun goes west-east. As that is happening, you know, we're time shifting the renewables, and we're able to then switch transmission flow on this corridor, 3 gigawatts of power that we can move back and forth. Could you imagine during the cold weather event that we had in Alberta, if we had a 3 gigawatt instantaneous back and forth? The other thing this link is able to do, black start. If there was any reason that WEC has a system-wide blackouts, they are completely asynchronous from the network next to them. We could use this system to black start the grid. These are all about the resiliency, about what we can do. You know, another project that's connecting PJM and MISO is called the Sioux Green Transmission. I actually love this project. This is a 2 gigawatt interconnector, but we talk about grid resiliency and using unique applications. We know building overhead transmission lines are hard. What this project is doing is that they're actually co-locating a 2 gigawatt HVDC system in the same right-of-way as an existing rail, right? So you can imagine the permitting, environmental permitting, right-of-way access, everything has been solved. You know, a good example is that we have another project we're working on, overhead line, 700 kilometers, 10,000 permit issues on the environment. This one, it was 500 kilometers, had 5. Right? So we have to think about other ways that we can look at doing these type of transmission using the technology. You know, a really good example that we have in the province of Alberta, we have the Edel and the Wattle. I talked earlier about the impact that wildfire has on insulation. You know, using a transmission line like HVDC, normally running at 500 kV, it has an insulator, let's say that's X long. So that's effectively the protection we have against pollution. An HVDC link can run at 70%, so we can drop the voltage down to 350 kV, effectively allowing a reduced amount of transmission. But you know, when Manitoba had those fires, we were turning off transmission lines. With the HVDC technology, we can reduce the capacity and allow us to go forward. So what I just want to sort of leave the room with here is, you know, there are a lot of issues. We're in a very volatile market. It hasn't been made easier. I do really want to point out that I was at a seminar in Austin, Texas a few weeks ago, and I think the strength of the grid is the cooperation we have through groups like NERC, through WEC. You know, it's a very collaborative environment. I think, I can't remember who mentioned on the panel before, but you know, we're so interconnected. We're not going to separate, but we also have to rely on projects like this, systems like this, to really build that resiliency. Because again, speaking from experience, in Manitoba, major issue with wildfires. Alberta with the cold. If we were able to increase resiliency through smart grids, distributed energy resources, interregional transmission, it will play a huge factor in going forward in resiliency that we're looking for. Thank you very much.
My name is Evgeniy Gorelov. I'm a director of asset management wildfire mitigation. If it gives you a little bit of a hint, wildfire mitigation is really a big concern for our utility. And so my presentation, and you will see it, a lot of themes are very similar to what you have heard, but we are deeply into less of a research and development, but actually application of tools, scientific tools to help us make decisions. But before I go forward, and being a local, I would like to start with acknowledgement of traditional land, and that FortisAlberta acknowledges that our operations and facilities occur on the traditional territories, meeting grounds, and traveling routes of Indigenous people, self-treaties, territories, and Métis people of Alberta. And we make this acknowledgement as an act of reconciliation and gratitude to those whose territory we reside or are visiting. Give you a little bit of a context of what company we are. We serve about 500,000 residential, commercial, and industrial customers in Alberta, all the way from the border of the United States and all the way up to kind of Athabasca, Conklin area, with a couple of carve-outs for our friends in ATCO there. So we have about 1.1 million power poles and 133 kilometers of power lines that we manage and build and try to make sure that our customers get good reliability and good service. As you can imagine, with this footprint, our needs are very diverse from one area to another, and the impacts that we're seeing in our system tends to be very, very diverse from extreme events and from wildfires in particular. Now, I'm going to talk a lot about wildfire piece of it, and I'm going to talk specifically about our use of situational awareness tools. But you can go about resiliency in a lot of different ways. And there's a fire wheel there. I'm not sure how visible it is, but if you think of it, I'm going to use just an analogy. If you built a house and you planted a garden for one climate, and now you live in a completely different climate, and you find out that you could, of course, rebuild your house. You could change your roof because now you're getting hail. Maybe you change your siding because you get a hail. But it is expensive, and it may take you quite a bit of time to do these types of changes to your house. But if you do know that the hail is coming, well, at the very least you could do is probably take your plants back inside the house and maybe cover your tomatoes. So there's things you can do with the situational awareness and more of a kind of operational level that increases your ability to withstand these events and respond to them. And essentially in a changing climate, there's a climate science that shows us where the climate is going to go. And we have done some studies, or we have done some work in that regard as well. But it is also a last line of defense, because you might be seeing events you have never seen before. You might be seeing events you have never designed for before, and you might be able to limit the amount of damage that happens to your system, or maybe to public, through the use of operational means, as long as you're able to see that event coming your way. And so that's where our use of situational awareness tools come in. Just wanted to add that on a wildfire front, we are not only concerned about the impacts to our system, and the impacts to our system can be significant. We have seen some significant events in the past few years. We're also concerned about impacts to public. The electric distribution transmission system is essentially an ignition source that is always present out there. And given the right conditions, and given a right type of a fault, it can be a source of a catastrophic wildfire. So a lot of our effort is also designed to prevent us through operations or our system from causing wildfires that could impact our communities. So I'll start with some mundane stuff. I'll show you some stuff that I think is kind of cool, but I'll start with a little bit more of a mundane. We use almost every public source available to us when it comes to short-term predictions. And all of these public sources are being pulled into our own internal system that combines them and helps us to see if we have some red flags coming our way. It also helps us make certain type of decisions, and we have numerous overlays built into that system. And when it comes to situational awareness tools, we generally find that more information is better. Like, I mean, a lot of information probably bad because you got to go through a lot of it, and sometimes you will have discrepancies between different sources. But if you're relying on one system, you may not be, might be missing events coming your way. And I'll show you an example of that too. We also produce essentially a high-level weather forecast. Not internally, we have a separate contractor doing it for us. And there are a couple of reasons behind it. It also gives us access to meteorologists and meteorology resources when we need. So we're not just relying on public sources, but we can go to people who are working with us, understand our needs, and they can do things like spot forecasts for us, or just go through with us what we're seeing, and if if they agree, or maybe there is another way to interpret what we're seeing as well. We brought very recently, we started working with a company called Technosilva, maybe familiar to some of you, and their tool is actually quite interesting. It's underpinned by a custom numerical weather prediction model, and out of that model, and it's a high resolution 2-kilometer model. Out of that model, they generate a number of indices, including the Canadian forest fire danger indices, such as daily FWI, and some experimental indices as well, like hourly FWI, the Fire Weather Index, which is based on some research that was done at the University of BC. And in addition to it, this tool is able to answer what-if scenarios at a large scale. Given the weather predictions for the next day, or day 2, 3, or 4, or 5, if a fire were to start from a distribution asset from the power line, where would it go? What would it impact? How fast would it spread? It can be used in the reverse as well. If the fire is, fire is already on landscape, it could answer questions: what's the likelihood of actually getting to our own assets? And how much time do we have approximately to respond? So we can do certain things with that information that can help us protect our own system. We are deploying our network of weather stations, not research-grade stations, but good enough to, and they're compliant with Canadian meteorological standards for fire weather data calculations. It's nice to have all these models in place that can forecast weather, but it's also very important to be able to see if what you expected is actually coming your way or not. Some of the decisions that we do make require quite high-resolution weather. Like the public weather stations we have today, typically an hour late. So if you are trying to make a decision based on public weather stations, you're typically an hour late with that decision. And some of the decisions we make, we would like to be actually ahead of what is happening and not behind. So we planning to deploy probably about 100 of those stations by the end of 2026. They're co-located with our assets. We've done some work with meteorologists to determine where the good locations for these weather stations. So they will be closing some of the gaps as well in the existing weather station network in Alberta. And all the data is publicly available through Synoptic platform. We also have a tool to actually give us warnings. It's essentially an alert tool. When some of these events, like a wildfire starting or a lightning strike occurring happens, that tool in real time gives us information where it happened. And if we have an outage at the same time, it has a capability to tie the two together. So this is, we didn't build it internally. We actually went out and bought it primarily because of the cost. Sometimes utilities make decisions, counting dollars, and if I can do it cheaper with some other guy out there, that's probably what I'm going to do. Finally, we also are doing some cool stuff with a new vendor that's relatively new to the world of utilities called GridScope. They build sensors that go on the pole, independent of the power system, so they don't require actually to be connected to the power system because they operate off of a solar, and there's, I think, is a supercapacitor in there, or maybe a battery. I forget exactly which. But these sensors give us visibility into our system during extreme events. Because if the system is de-energized, the way utilities have been operating before, like as soon as your system is de-energized, you lose complete visibility of what's going on out there. And if you are out to fix that system and you are in some high-risk wildfire conditions, you can't necessarily just fix one thing and re-energize without having a risk of something else failed while you were working on your system. So this technology is actually capable of giving us information during blackouts. Tell us, while you were fixing one part of the system, actually another part of your system failed because the tree fell on top of it. Very, very interesting technology for utilities. We have seen some results out of it. It's very precise. It is not very cheap, though. So, for now. Still good on time? We're out? Okay. I'm actually at the last slide, essentially. All of this feeds into how we operate our grid on a day-to-day basis. We could do several things. We change how we actually work. So if we're in high-risk fire conditions, we might not do certain type of work. We might not drive certain type of vehicles. We may not idle on the side of the road. We will carry, our people will carry firefighting equipment, and they will assess the risk when they do the work outside. We also change our protection settings in our system dynamically. So we will change the sensitivity of our protection devices, or we will block reclosing in our devices to prevent us from causing ignitions. And that's all being done on a daily basis. Every day we're doing this exercise, and every day we're making these decisions, and based on that, we run with it. And one more thing we do is we use this information to prep for outages. I have an example of May 29th, had a pretty significant windstorm here in northern Alberta, with some weather stations recording 130 kilometer-hour gusts. At that speed, distribution poles tend to snap. We had a few of them snap. We had significant outages happening at the same time. And we used the TechnoSilver tool because that was the only tool actually was showing us that it was going to happen to prep for this event. We moved resources from the south part of the province into the north part of the province. And that, by our accounts, reduced our restoration times probably by about half a day, maybe 12 hours. So if we would not have done this, would not have used the tools we had, we would have been restoring power for another 12 hours for our customers. But because we were able to see this is coming our way, and we knew this is going to cause issues, we were able to respond proactively. That's it. Thank you.
Okay, hello everybody. Hopefully you can hear me okay. Again, my name is Everett Stuckless, Manager of Operational Resilience with Enmax, specifically with Enmax Power. One of the benefits of going last is everybody, the wonderful panelists here, have definitely set the stage for me, and I did promise Rob that I would try to be quick to keep us on time schedule, so I'm going to see if I can adhere to that. But thank you. So a little bit about Enmax, if you're not familiar. So Enmax is our company brand. It is our parent company's single shareholder, which is the city of Calgary. We also are made up, though, of what I would call several smaller companies or different business lines underneath that. So we have our competitive side of the business, which is Enmax Energy. And then we have our regulated side of the business, which I'm part of there, Enmax Power. We also own the Versant Power in the state of Maine in the eastern United States. So from the context of where I'm coming from here today, really just speaking towards the wires and stations side for our service territory, which is the greater Calgary area. We are definitely an urban utility, so we bring a different perspective than you'll see from some of our previous panelists. And we also don't consider ourselves to be typically a wildfire exposed territory. We do have things like Fish Creek Provincial Park in our service territory, as well as some other, what I'd say, grasslands. But typically we don't focus on wildfire as one of our severe weather threats, at least not one of our direct severe weather threats. added in this slide just for myself, and it's a little bit of an introduction, but what really I'll focus on is just to highlight what operational resilience means to myself. So it's a combination of both reactive, preventative, and proactive pieces. Traditionally, the electrical sector has really been a reactive sector, I'd say. We have been a slow-moving beast for a very long period of time, and we've really focused on preparedness as one of our main incident management and even risk management tools. But one of the things I've been known to say more often than not is preparedness does not promote meaningful change. That really is just to say that we need to do more than just prepare. Preparedness is focused really on things staying in the status quo. If you have a plan, you practice that plan, you get really good at that, but that only works while things are status quo. And as we know, the world is changing on us very significantly, fairly often. Some examples for us from a Calgary perspective here, we've got on the left side, you'll see snow timber. You also see some photos there from the 2013 Calgary floods. I do still find it quite amusing that bus is trucking along Elbow Drive, no problem, even though it looks like there's at least 4 feet of water there, so credit to the city for that. And then in some more recent, we've got the hailstorms from last year in the center there, which is fairly damaging. So the takeaway here is that we do have great reliability within Enmax Power, and we do have a very strong incident response program. Our plans were not sufficient for these types of events, and what we're starting to see is these events are more frequent and unfortunately also increasing in intensity. So we had to take a different approach to how we look at this, and not just preparedness, but also trying to design and engineer resilience into our program. And what that really means is that we're trying to take a more holistic approach to designing resilience into our infrastructure and making the incremental improvements where we can. If you're familiar with the utilities, though, and how we make decisions and how we implement projects and make changes, there are several challenges that we have to deal with there. Affordability and reliability are a constant balance. We could spend exorbitant amounts of money to increase reliability and maintain constant connection for our customers, but it would probably put us in a situation that nobody could afford, including us. We're also looking at long construction supply chain timelines, which make even some of the basic improvements a lot more challenging. Increasing interconnection and interdependence challenges. We've got rapidly changing technologies, so in how we review some of our project plans and funding submissions, by the time we get around to actually implementing that might not have been our first choice anymore, and that is becoming increasingly more likely as new technologies get onboarded or even come to surface. If part of that might be already obvious there too, we've got the regulatory uncertainty as we make those decisions. Even if from a climate resilience perspective, there's regulatory uncertainty on what we are positioned as a province and a nation to tackle. But from what we view on that, what we can really control the most for ourselves, other than that balance of affordability and reliability, is some of the climate uncertainty pieces. So there is data available, and there's modeling techniques that we can use to try and eliminate some of that climate uncertainty in order to better position ourselves to make intelligent decisions as a utility. So we've embarked on a project with a combination of partners, in particular the University of Regina and their PARC program has run some modeling for us in terms of long-term environmental monitoring for the greater Calgary area. Initially there was hundreds of variables being analyzed in this model. I think it's actually up to a couple thousand now. It's very detailed, and it's forecasting out into, I believe, the year 2938 currently. We use the Simon Fraser University supercomputer to run some of the models in 2023 as proof of concept. Got a tremendous amount of data from that, and the huge challenge that we realize is once you have the data, you have to do something with it. So analyzing the trends and trying to parse what we think is realistic from some of that data that's emerging is now the challenge, and we've gone in and we're actually running now, I believe it's the third iteration of that data to help focus in on some of the variables that we view as important to our utility. It is in partnership, again, with the University of Regina, but also with our shareholder, the City of Calgary. So as we progress, a lot of the information that we are developing does become publicly available, and we actually, instead of dispersing that information as Enmax owned, we work it through the City of Calgary and some of their publicly available climate databases and pages that you can access through the City of Calgary website. One of just as a simple example of what we are looking at here is, so here's just the daily temperature average that's simulated from the analysis that we've done. And I apologize, it's tricky to read. This is one of the better graphics I was able to get a hand on. But what it's supposed to illustrate is even within the, you see the city of Calgary limits there, kind of the jagged box on the inside, is that temperature is pretty variant across the city, and the difference there that we see from the extreme weather threats in those different temperatures can be massive. It's not unlikely that you'll see high winds in the northwest and then hail in the northeast with strong rain or heavy rain in the southeast, but never those patterns overlap anywhere else in the city. They deal with one particular threat at a time, and we want to look at our assets and infrastructure to meet those challenges specifically as well. We can't just put in something that performs well in one condition if it doesn't actually meet the weather threat that asset might have to take on. So we're working our way through developing some resilient strategies there and integrating that deeper into our design and engineering planning, and hopefully it will continue to be integrated into our infrastructure, and we'll be able to maintain a high reliability for the city of Calgary and the other customers that rely on us. And I hopefully kept up with what I promised for Rob. Thank you.
There, I think I got it now. Great, thanks to everybody. Outstanding panel. Got some good questions.